have the honorable job of being between you and lunch, so I'll try to make it short. So as said, the talk, can you see it? Yeah, is about learning sparse model at scale. And actually, I think it's a bit of a mistitle. It should be saying learning from sparse data at scale. And you'll see in the talk what I mean by this. So to recap a little bit and also see how my hairline progressed over the years, I did study in Berlin. I'm a computer scientist by training, as well as a statistician. And one thing that I particularly like is bringing machine learning into industry products. And so my experience, and this is what I'll kind of talk about in the next 30 minutes, is reflecting back on the last 12, 13 years where I worked at Microsoft Research, at Facebook, as well as at Amazon, where I'm working now. And the context of a lot of the lessons learned that I will share and algorithms that I will describe are in the context of 4 applications that you may or may not have heard about, but they're fairly visible. One of them is the matchmaking system that was for many, many years in use on Xbox Live. So in particular, I don't know, how many in the audience have played Halo, the video game? Wow, this is more than typical. Depends. Different audiences, you have it the other way around. Almost everyone played. So matchmaking, bringing people together online. That was one of the systems that was had the pleasure, the honor of being part of the team working on it. Ads on web search. So you have a web query on Bing and all the ads that need to be shown. A system that when it went into production ran for several years, 3 years at least, and predicted every single time a request came for an ad. Facebook, I think many people, how many people here in the room use Facebook? Still smaller than I would have thought. Is there trouble for Facebook around? So all the nice ads you see in Facebook, the scale of this was rather ginormous. So you see it's almost 1 trillion ads that had to be ranked on a single day on 1 billion users. So that's the scale of the systems that we developed. And then work at Amazon on demand forecasting for fashion. So every single time you buy a trouser or a shirt, Amazon has already tried to predict how many of them will sell in the United States or in Germany or so far in order to manage the supply chain. So this is the technical background of the talk. And the talk, I'll start around what is sparse data and why is models for sparse data, why are they so important? And what is the general toolkit for both modeling it and deriving algorithms? So the kind of toolkit I describe is very much the blueprint, the Lego bricks for the systems that got developed in those 4 applications. And then I wanted to share in the second part 3 of the major lessons learned. One of them around the resource constraints, something that we don't think about much when we think, sort of more in a scientific setting about a machine learning algorithm, but it becomes very relevant when you go in production at scale. Second one is how do we scale things up? Because around 5 years ago, data sets got so large that single machine solutions didn't work anymore. And then how can we actually combine the bests from modeling dense data, and I'll come in a minute what that means, with sparse data. And then conclude with some outlook, what I think is interesting future directions. So sparse data models, where does actually all the data in machines that we use for machine learning come from? And in the simplest form, of course, we have a sensor. So this could be a camera. And the sensor has some physical readings that get interpreted by code. And that code then generates a data set. Now, the interesting thing when you look at computers is that what are the sensors? So by far oldest sensor in a computer is actually the keyboard. And when you think about where is your identity in all these online services established, it's established by you logging in, you typing your name into a text box. So the data that we analyze was typed in. There's no biometric blueprint we took. Another old sensor is the microphone. And I think we see the resurgence of analyzing this kind of data. You see this coming now, as well as the video camera. The first webcams are dating back to '94. I think since 2000s, it's very common to have webcams. They provide different kinds of data than what comes from the keyboard. And then more recently, we have location sensors and biometric readers that are available en masse. Now, if those sensors get interpreted, ultimately what generates the data that we analyze in machine learning is code. And that code comes in 3 flavors. Some code that interprets the raw signals from the sensors, so the intensity of the button that got clicked, or just an encoding in ASCII of that character. So that's filters for the sensors. Unique identifiers. That's something that is, we don't often think about it, but when code needs to generate something to identify an entity, a virtual entity or physical entity, code generates those IDs. They're not some physical readings, often not physical readings. And then a law of code is often there to just communicate information. So the information is stored on some server, on some other computer. So the remote process communication generates data. And data sets is a stream of records. So I often think of it as a big Excel table. And now the columns have a certain type. And in measure theory, the types that you consider for data is fourfold. It's nominal. So a nominal data, on a nominal scale data, you can only check that two data items are the same or not. Ordinal, so you can check that they're the same and they have a natural ordering. For example, if we look at an outcome of a game, or if we look at the star rating, 3 stars is more than 2 stars. But if we look at the name, Herbrick is a very different name than Schmidt or Fu or Smith, but we can't really order them. And nominal and interval and rationals, these are scales for data where the operation of taking a difference or taking a quotient is a meaningful one. And the interesting observation when you, oops, that kind of went. The interesting observation is that most data that you actually analyze today is data that comes from data about people, about places, about organizations, is of nominal scale. So how do you represent data of nominal scale? Meaning it is actually, all you have is an identifier. Data in books, words, is of nominal scale. So how do you identify it? And the way to represent nominal scale data, one of the most powerful ways is if you make observation vector O of just identities, you can sort of represent it in a sparse vector. And the idea is you have an identity vector that gets indexed by the particular observation you made. So you have a stack of lots of sparse vectors. And to give you a sense of the scale, if we generate one of such vectors for a task where individuals, like per person advertising is involved, you have a billion-dimensional vector if you work at Facebook, or you have a 250 million-dimensional vector if you work at Amazon and look at those customers. But almost all dimensions except one is actually 0. So if you now do an operation, like the simplest possible operation you can think of is a linear product, an inner product. So you have parameters that a model needs to learn. Let's call them a weight vector. And you simply want to compute the inner product between those two. Then what turns out is interesting is that each of those components becomes very meaningful. You can interpret it because it corresponds to the influence that particular dimension, that particular name, or that particular place has on the rating, on the prediction. And it's dense, but the actual operation is never implemented how you would naively do it. Like in school math, you would multiply every dimension with each other and then sum up. For sparse data, it's a completely different operation, which is that the inner product that you do becomes a dense vector lookup. So your model is dense. That's why I said at the beginning, we really talk about dense models. But multiplying, computing an inner product actually ends up being the basic operation you need to compute on hardware instead of a lookup. You look up, and the index is the particular nominal scale observation you have. Now, given we have represented that data, how can we model it? And one of the most powerful models that I found in my career is that of graphical models, which doesn't necessarily mean you have to be a Bayesian, but it's a very powerful way of representing the generative process of how the data might have arrived. And the idea of a graphical model is that both the data and the variables that describe how it's generated are actually represented simply by a round circle, and there's dependencies between them. And the dependencies should translate to time computation. Because in practice, your code, your algorithm has to run on a computer. And the variation of a graphical model that is powerful to be able to express that is a vector graph. Vector graph goes back to the late 90s to formally describe that. The idea is really that you have a bipartite graph. That means every data or latent cause variable is only connected to vectors. And the semantic of the vector graph is that your function you optimize over, either you maximize it or you will see you some dimensions out of it, has the property that it's a product of these black squares. And the black squares only depend on the round squares to which they have an edge and they're connected to. So for this example vector graph, we're talking about a function that has 3 vectors, f1, f2, f3. The first one only depends on A, the second only on B, and the third one depends on all A, B, and C. And what's nice about that framework is it's very simple to explain, to understand. You go away from reasoning in algebra to reasoning on pictures. So often the flow diagram of how data could have arrived translates directly into a model. And what's even more nice, and we see that there's almost a blueprint how to go from a model to a special algorithm for that type of data. So if you look at the simplest possible model, classification. So our data is of nominal scale. We have people IDs, we have people places, we have times. If we now want to classify, the simplest model is that we have an inner product between the parameters we need to learn, W, and the observation, which ends up being a vector lookup. And the probability that we observe a yes, no, or a click or a non-click in an add setting, or a win versus a not win in a game setting, is simply the probability, the probit function, so the integral of the probability of a Gaussian up to the point of this inner product. So in a vector graph, you'd basically specify a lookup operation to which particular components of the weight vector are relevant for that instance. Then there comes the summing operation, and the latent variable z is then getting fed into this transfer function that goes from -infinity +infinity to 0% probability or 100% probability. So a slight generalization that we use in almost all recommendation settings is when we have nominal data, so that's sparse, so x and y are these sparse vectors, and we would like to, but they are fundamentally different. One of them is all about users, the other one is all about items in a recommendation setting, or entity type 1, entity type 2, and you'd like to build a model that is capable of learning what to recommend for what type of users. The one simple model is to say we're mapping the users, the x vector, in some latent space S. We're mapping the items in some latent space T, both of them by simply an inner product operation over more than one dimension. And then when we take the inner product between those two, we have a latent variable which indicates whether or not they're yes, no, or they're ranked in a certain way. So in pictures, it's probably easier to explain than in math. You have your indexes from sparse data index, which particular column of the U matrix you need to look up. Then you sum those components of the U matrix together. Same happens for the V matrix. So it's simply a lookup. Remember that computationally, all we're talking about is looking up elements of that matrix. And then the latent operation is multiplying the components of S and T together with a multiply factor to obtain a rating R, or a variable that we can now use for classification or for ordering, so forth. We can combine these two. Then you get what you might call a contextual bilinear model. Again, super easy to explain. The bottom part is what we had in the first. The top part I had in the second slide. And as you will see later, each time you change the overlay of this, the layer of this graph, you end up with a variation of algorithm that is optimal for this data model. Ranking. I talked about Halo and online gaming. So the idea is two players play against each other. One way to describe in algebra what's the likelihood model of an outcome is, given two skills of two players, the probability that one of them wins over the other is proportional to the chance that the performance that each of these two players have are in this order. And the performance varies, for example, like a Gaussian around the skill. So in pictures, it's very easy to describe. Skills is what you observe. Data is always great. And you assume that the outcome which you'd like to sample is simply flowing from top to bottom. If you have more than two players, you have two teams, you can make a simpler assumption and say we summarize the actions of two teams. Again, remember that the lookup is within the dimensions of that S vector. So it's all a sparse matrix multiplied to get to the S vector. Summing those two dimensions up, and then depending on which of T1 or T2 is bigger, you would generate with this model either a win or a loss. If you had more than two teams, you could generalize this further. Mathematically, it's the same. You see pictorially now you get a combination of all the possible latent performances of the teams with each other. However, your data, when you make online gaming, is the other way around. Your data, the gray thing, is actually the outcomes. So if you observed first team beats second team beats third team, then the variables you'd like to learn is what the skills are. And you now end up with a tree that is basically the sequence of pairwise orderings, which we can translate into a vector graph by simply translating every one of those conditional probability distributions into factors. And again, we have now a blueprint of a model for nominal data, which is the identities of the people that played. And the data is different. This time we learn which person was playing in which team. That defines the edges between the T variables. And then which team came first, second, and third. That defines the edges between the T variables with each other. So all that the data was really doing is it defined the edges in this graph. Third case, which is forecasting, which I mentioned. Imagine you'd like to forecast. So one simple model is that your data represents which particular product, in which particular month, in which particular market, in which particular price reduction. That indexes, that's all encapsulated in this X vector, that's sparse. You'd like to predict you'd like to model the number of units demand, and if you kind of a model that's quite typical is you model specifically no demand at all, 0 units bought, 0 shirts sold, 1 shirt sold, 2 shirts sold. But it's a time series, so like a Kalman filter, you assume that there is some latent state that describes 0 demand, 1 demand, 2 demand from time step, from day to day in which demand happens. So you end up with this rather complex picture where the top part is the latent variables, those that you need to model a time series. The bottom part is what you might call your model of the data, the likelihood. And because it's all nominal data, the lookup was actually a sparse vector multiplier in the top. Now how could you, I said the whole time along, you have these very different data models for time series and demand, or for outcomes of matches, or for classifying a click happened or it didn't happen, or recommendation in the marketplace. How do you end up with so many different algorithms? The trick here is that this operation of summing out those variables on the top can actually be very much automated by observing that you use one simple fact, which is the distributive law, in the right way around. So the idea here is if we wanted to sum out all variables but the W variable, so W is what interests us, and we have this relatively simple vector graph, 4 factors, F1, F2, F3, F4, then if we do this algebraically, we basically have a sum over the first variable, V, 1 over X, 1 over Y, and 1 over Z. So we have a sum of a big product, and unfortunately, if you actually write this in code, you'd write 4 nested for loops, and if you had 100 variables, you had 100 nested for loops, and it would be exponentially many execution cycles before this finishes. But what's nice is what you see here is if we were to do this sum, you can actually pull one of those terms out. The first one, F1, doesn't depend on X, Y, or Z. So in reality, you can turn this thing into a product of sums by simply using the fact that A times B plus A times C from school equals A times B plus C. And so if you do that, you end up with an expression that has 2 partial sums. The partial sum is all the sums over V, and then all the sums over X, Y, and Z, because they're separate. They're getting separated by the fact that you're interested in W. And we call them messages. They're basically a basic data structure you need, and that arises in the algorithm that you end up with. And then you use the rule again and again. And what's nice is you arrive at an algorithm that has 3 simple recursive steps that peel each of these graphs that you saw, whether it's a recommendation, it's a classification, it's a ranking, or it's a forecasting setting. They peel that graph off from left to right or from top to bottom. And in the peeling off, you apply the first and the third rule, which have the nice property that they're always accurate if you use Gaussians or betas or binomials or anything that's in the exponential family. And you have this application of the second one, which is where some of the tricks come in approximating algorithms for inference. Now, I said you don't have to really be a Bayesian. What I meant by this is that the entire algebra trick that we used for this, that was used, is encapsulated in this simple equation. So all we did is we really changed A times B plus A times C into A times B plus C. Seems very simple because we all learned that at the 6th or 7th grade. What's nice about this thing is, on the left side, we have 2 multiplication and 1 addition. On the right side, we have 1 multiplication, 1 addition. So we have a 30% reduction in complexity if we were to implement this on a computer. Now, we've done this recursively. Again and again, we've applied this. So what that means is when in practice, you go down from an exponential number of algorithmic steps to take to a linear number, only as many as there are edges in this graph. So if these graphs have not many edges, you end up with very efficient algorithms. And almost all machine learning algorithms in existence today can be explained with this framework. Now, what's even nicer is all we've used is that A times B plus A times C equals A times B plus C. This is also true for not summing out stuff, but for maximizing. If you simply wanted to have an algorithm that learns the most likely weight vector, or the most likely mapping matrix for a recommendation setting, or the most likely states in a hidden Markov model for a time series. Because the maximum of 2 products, the maximum of A times B and A times C, is A times the maximum of B times C. So everything I explained can not just used for summing out, if you're more Bayesian inclined, but also for maximizing if you're sort of more for optimization tasks. And I think that's a great insight. And as I said, it's almost a blueprint for algorithms. The algorithms come from the model of data. Now, I said I'm going to talk about 3 lessons that we've learned, or I learned, particular when working on this. So the first one is a resource constraint reason. And one of the things that's interesting when you want to bring such algorithms into production, resources do matter. And what I mean by this is when you, one of the resources that's very important is time. So when you create an online service like Xbox Live or Facebook, you have to obey a maximum time you cannot exceed when you compute the candidates you need to return. So when you type a web search query, you typically have no more than 5 milliseconds, and then the results have to be delivered to the web page of the user, so they're not sitting there and waiting for search results to appear. Or when you're going on Facebook and you check right now, then in under a second you have a new view, the most recent view. So how did that happen? Well, what happened is that in under 5 milliseconds, some machines had to sort through candidates and choose which news stories or which ads to show you, or which search results in a product search. And when you think of how long does it take if all that data is stored, if we store that weight vector in memory, all we need to do is we just need to look up an index. So the fastest way you can look up an index is about 10 nanoseconds. So if I have 10 nanoseconds and I have 10,000 candidates to simply score, computer score, learning has already happened. I only have about, I can only consider 50 lookups per instance. Now you might say, what's the 2 angles I can play with? Well, one angle I can play with, I can minimize the number of candidates that I need to score. And so the industry practice here is to say we do an L1 ranker that uses 2 variables, and we've gone from 1 million candidates to 100,000 candidates. Then we use an L2 ranker that uses 4 variables or 5. But the problem you see here is a lot of the models that sometimes get discussed these days that have a lot of computation per candidate exceed the time budget. You're exceeding 5 milliseconds, you might have the most accurate algorithm, but it's non-practical because the web page cannot be rendered. The second constraint comes in training. So we've got more and more training data. I think there was an example earlier, 1 trillion data points, or 100 billion to train from in an ad scenario. The problem is if we look at the 1 billion examples per day and remember that the day's got 86,000 seconds, and remember that we need to change. Learning is all about changing parameters, changing the weights, computing these messages, even if it's just additions and multiplications. We really only have about 800 writes that we can perform before the speed of changing the state of a memory cell is a physical limitation. And so the reason we cannot learn, even if we have a computer that has loads of RAM, like 1 terabyte of RAM or 2 terabyte, is the fact that there's some sequentiality to the way we have to access this. And these constraints really do matter in practice, particularly the first one, which is you cannot exceed 5 milliseconds. Now the second constraint that's often overlooked, again that speaks for sparse models, is cost. And just as an economics background, economics 101, profit equals revenue minus cost. So if you run Facebook, your profit is how much revenue you got from people paying for the clicks on ads, minus the cost of running Facebook, which is salaries, but also data centers, computation, cost for computation. And unfortunately, or fortunately, businesses that have a negative profit are not viable in the long run. Okay, so if that's the case, then let's look at Facebook. So this is all public figures. The annual revenue last year was in the order of $18 billion. So $18 billion paid for serving ads. Per day, that's roughly 50 million. On a single day, over 1 billion, close to 1 billion users are actually visiting Facebook. And there is a blog post that says that at least 1,500 stories, 1,500 entities that contain words and people identities have to be computed in order to show you the 300 news stories that all of you on average look at each day. Okay, so the computational need is 1.5 trillion scores that need to be computed on a single day. And if we were to use the entire revenue, so there's no salaries, we don't serve ads, we're not acquiring companies, so everything gets served for newsfeed, you have 3 microdollars. That's the amount of money you can spend in computation for a single training, storage, and scoring task. And that's and I'm bringing this up as a bit extreme. It's probably even smaller. But the reason I'm bringing this up, this is an important consideration when you think about, okay, let's use very accurate algorithms, but the cost of them, particularly in the prediction phase, exceeds, is extraordinary in comparison to the gains you make. So in practice, time and cost are very important constraints. If the cost is too high, the entire ads model is no longer viable. If the time is exceeded, the customer no longer gets any experience. The second thing, and it ties back with the scaling, particularly when I look back from 2005 to now, we did get to a point that a few years ago that 1 billion examples and throwing data away was not really a viable approach. So what are you gonna, oops, that's not good. So what are you gonna do if you really do need to scale up the training algorithms? And yeah, I have a few numbers here that are fairly extraordinarily large. So for example, we have forecasting there, and what you see there is 30 million products that need to be forecasted each day. You have about 1,000 days in the past. So that's 3 billion examples to train from in a single day. Or the scale of a Facebook news feed is in the order of 300 billion examples to train from in a single day. So you can no longer physically, it's not possible. You would exceed the time of a day to train from the data of a day, even if you buy the fastest computer that's available. So the idea here is, again, we resort to factor graphs, because that's the powerful thing. That's why I like them so much. The algorithms, even things like parameter server, directly fall out of them. And the idea is that the kind of model of data we have, data is the gray in the bottom, is that there is a single parameter, we call this a conditional model, that your parameters and your data can be grouped together. So it's a way, mathematically, you kind of group the factors that handle the messages from the data, and you group the factors that handle the messages to the parameters. So a top part is the parameters. And each of them you embody, literally, in a computational service. So the idea is that the top parts, the top groupings of the factors, are services that handle the parameters, that handle anything that goes to and from the parameter changes, either prior settings or what from the data. And the bottom parts handle all the computation you need to summarize the information that's in the data given the parameters. Okay, and you can see in the picture it's kind of easy, and you can map those. You can map the data model directly to a physical model on servers. So the way you do this in practice, and the whole area of research is called parameter service, is that you literally have two logically different services. One of them implements all the message computation, this maximizations or summarization, marginalizations, on data. So that's what MapReduce mostly does. So it puts the computation where the data is. But you have a second logical service that actually performs all the computation that's to do with the parameters. And you use a typical network layer to communicate, meaning when data induces a change, these messages are a change to the parameters, they get sent over the wire to this to the services that handle the parameters, and then the parameters themselves send their state into caches on each of the machines that are typically storing the data and processing it. And one of the smart things to do here is if those parameters, the caches and the true ones, get out of sync, algorithms diverge. So it's very, very useful for each of the data processing slides to actually know what is the rate of change of every single parameter. So some of the protocols for this networking take care of parameter service, can take care of this in order to avoid divergence. So the last one I want to talk about is, now if nominal data is so prevalent and can be modeled that way, how do you actually now do feature engineering for nominal data? And how do you do feature engineering when you don't have nominal data? So the simplest one is you already have an ID. You have a user ID, or you have a place that is tagged up in an open graph, or you have an hour of the day, or you have a category for a product. Well, you just describe in the feature transformation, ID transformation. What's nice about it is it's a constant overhead to describe it, and you end up with the same number of values that your original value set had. Often that's not powerful. That's of course not powerful enough to really get high generalization. So next one is if you have a real valued observation, like for example, time of the day, you could bucket it. And the idea of bucketing is if your interval scale observation is a single number, you have a process like clustering, one-dimensional clustering, to learn the bucket boundaries. So boundaries that basically put those real line into segments, contiguous segments with each other. And with describing order k boundaries, you get order k values, the values being that my observation in the interval scale was in that bucket or not. Okay, if you have more than one dimension that's on an interval axis, you can do an n-gram. So what's an n-gram? In pictures, and as you probably noticed by now, I really like pictures over algebra. In pictures, it's basically you take a grid. So if this is h and this is time of the day, you now discretize the h, discretize time of the day, and what you end up with is a lot of squares. Just you might call it a Cartesian product. If this is 3 dimensions, it's a cube, but it's sliced. It's sliced sort of in the same width on each of the dimensions. And what's nice about that transformation, and that's why it's so popular, is to describe that transformation, you just need to say which 2 categorical variables do I cross. So you have number k. If you do k crossings, number k description length in your feature transformation to describe that in your search space to search that. And you end up with a large number, an n to the k, if you have n values on each of the x's, so an exponential number of values. So it's very good if you want granularity, if you want explainability, because you now get joint effects that, as a statistician, you would call joint effects you can model. There's one downside, you get such a high number of values for that nominal scale variable that often generalizations in the areas of the space where you don't have much coverage is pretty bad because it's discretized in every part of the region. When you look at that picture, you can already see if all the actions happens in the bottom right corner, you shouldn't have that fine granularity in the top left corner. So wouldn't it be better if you had something like this? So you discretize the space a bit more appropriate to where most of your data lands. And one way to do that, if you look at the picture, is you sort of have a split on the first axis at the second boundary, but then you only split once on the second dimension. And similarly on each of the other dimensions. Now what that's actually just using a decision tree on the dense data that you had initially. So one very, very successful approach that we've been repeatedly using is to use actually boosting not to learn the classifier or the ranker or the forecaster, but to learn the features. Meaning you take each of the trees that take your input data, your raw input data that does contain interval and ratio scale data, and each of the trees becomes a feature generator for a nominal scale data. What is the nomen? What is the dimension? It's which path does the observation end up with. So if your record gets classified by the first tree, it might end up in the first path, on the left. And by the second, it might end up on the third path, and so forth. So each of these trees is now basically doing what we saw in pictures before. It's characterizing one discretization that is much more coarse and appropriate for where you saw input data relative to simply n-gramming those. And then those trees become sparse data generators, which you can plug into any of the models we described. Good. With that, I want to conclude with 2 things. One is, what is interesting future directions? If nominal scale data is so relevant, so prevalent, and so powerful that you can model people's propensity to be good matches in online gaming, and you can rank ads that way, and you can do it all with the right cost model and with the right time constraints. Well, one observation is that when you look back, why is deep learning so relevant and so powerful today? I think one of the reasons is, you could argue it's the algorithmics, but they haven't changed. I mean, I recently saw a talk by Jan where he said, I'm using the same slides I used 20 years ago, and I believed him. But it's that we can now run experiments 3 orders of magnitude faster because we can use special hardware, we heard this in the first talk, that's actually capable of performing a dense matrix multiply through, fully in parallel, so 100 to 1,000 times faster than on a typical CPU architecture. But we don't really have any hardware for sparse matrix multiplication or something that's optimized to perform those operations we talked about in 2 or 3 orders of magnitude faster. And I think if we had, that might actually really also increase the speed of experimentation. The second one is that when you deal with identifiers, one lesson learned over each of and all of these applications is that the meaning of those identifiers, because they come out of code, they don't come out of sensors, changes over time and are very hard to predict. So my prime example was when we worked on the first-person shooter Halo 3, and analyzed that data, they had, it's almost classic, they had designed the space of identifiers for types of games only with 4 bits, and after a while it became such a popular game that they had to reuse the identity for a 2-player match to a 6-player match. But that wasn't obvious in the data, so all of a sudden you had completely wrong identity information. So algorithms that help to automatically detect when identifiers change meaning would be very powerful future directions. And the last one is sort of relates to the observation we've made by using decision trees to learn discretizations, but find something in the middle. N-gramming gives you an exponential number of values, which is great, but it's very easy to describe. So the feature transformations are very compact to describe. Now, it's too many values, but a compact descriptions. Trees give you the right granularity, but they're very long to describe. It takes as many bits to describe a tree as you have values in that tree. So learning methods for learning feature representations, that blending between these two is, I think, is also very powerful future research directions. And with that one, I want to conclude, I guess, with 3 messages. The first message really being that the vast majority of data that we analyze, even today, and maybe that's different in 10 years, is actually of nominal scale. It's not of the rational and ratio and interval scale, where dense matrix multiplication is a key operation. The second one is that resource constraints really do matter, and they drive the choice of algorithms. Resource constraints are the driving force when it comes to how long does it take, and is a certain business model actually viable. And they're as important as success metrics for machine learning algorithms as pure accuracy. And the third one is, one of the powers of these sparse data models is that they're interpretable. And when you make high impact decisions, like in a medical or in a health setting, then knowing what your model, or in a demand forecasting setting where you start automatically ordering in the millions of dollars, knowing what your model does is as important as having it accurate on some backtesting. Thank you.